Unfortunately, I'm in a bit of a brittle state throughout this conference, so I didn't really have a chance to prepare the slides. And so the context of this this session is that we, as the Swarm team, as the project scope grow, we kind of undertaken the task of providing some base layer services for Web3. What does this mean? We want to provide some services which cater for web developers to migrate their projects from the Web 2 stack to Web3. This includes node-to-node messaging, as you might have seen the Louis Holbrook's talk on PSS, and also includes some payment solutions or like infrastructure to run service networks using the swap, swear, and swindle paradigm. And thirdly, and very importantly, some sort of database support. Now, basically the Swarm team kind of launches some different working groups around different topics. One like today's session kind of nicely maps to these working groups. We have one working group around PSS messaging, one around streaming integration with LivePeer, one around the swap, swear, and swindle games paper, and fourthly, the database group. Currently, the most active participant in this is the company called Walk, who are we are very privileged to have them in the audience right now. So they dedicate a lot of manpower to this project. It's just launching. So I kind of want to briefly touch upon some aspects that we trying to target with this project. As you might know, Swarm underlyingly is just a chunk store. So the underlying network of storage just takes care of distributing chunks of fixed size to particular nodes in the network, and it retrieves those. And all the higher level API functionalities is built on that. So for example, when you retrieve an asset in your browser, when you retrieve a file, there's a mechanism which takes the root hash of the Swarm tree and retrieves intermediate chunks. From this, it recovers the next level of intermediate chunks, and finally, it resolves the files into the actual data chunks, which, when retrieved, they sequenced one after the other and give you the asset and that you can render in the browser. Now, in an even higher level, there's a thing called manifest, which is basically the tool that enables URL-based addressing of content over Swarm. It's based on having a so the root hash of a website is you retrieve a manifest, and the manifest is basically contains an index from URL, from path to hashes, which corresponds to a routing table in the original what you normally see on servers when you retrieve a domain. Then it basically routes certain paths that you see in the URL, and you resolve into hashes. But in the same way, this index can be thought of as an index of a database, because it's simply just associates a particular key that you can. It's the same as the path in the URL string to an asset or to a database record. So in this sense, there's already one very simple way to represent indexes or databases in Swarm using manifests. What this scheme is missing really is a smooth way to prove that, for example, an index generated from a original database is correct. So it does not contain spurious entries, and it does not contain omissions according to an original primary data source. And so one aspect that we would like to work on is to have this provable databases and provable queries and so basically this is a crucial feature that will allow the database services to be fully decentralized, because if you have or the database processes, for example, indexing is provable, then you don't need any kind of reputation system or any other mechanism to select your service providers, and it allows for a trustless service network to provide these services. So there are a few tricks which we can cut short this problem. So one solution might be simply to take SQLite, and SQLite has a file structure which you can simply store on Swarm. It has a configurable page size, so you can configure it to correspond to the Swarm chunk size, which is 4K. And the trick would be to have the whole SQLite implementation simply compiled to WASM and to Solidity, and then you can use TrueBit to simply prove that query resolution is correct. So that's one possible avenue. The other one is to use the latest implementation of the Swarm hash, which uses binary Merkle trees for the hash. The fact that we use binary Merkle trees over the chunks for the chunk hash gives us the opportunity to have very compact inclusion proofs to a very fine resolution of 32 bytes. So any kind of inclusion in a chunk can be proven, and the short proof can be verified then on the blockchain. So we kind of we're trying to come up with a clever serialization scheme, and together with the canonical serialization and the inclusion proofs, you can directly map, for example, statements like, you have an original data source, which let's say let's get an example. So, for example, you operate a flight aggregator site, and your customers are or your data providers are like travel agents which publish their flight offers, and they want to make sure that if they publish a flight offer, then their offer will be included in the current search results on the flight aggregator site. So what you do is you register, for example, your primary data source where you publish the offers, and the indexing service that aggregates these data sources and produces a common aggregate index can be tested against statements like this particular offer from like Cancun to Mexico City at this price by this airline is actually included in the aggregate index, and if we find a clever canonical serialization scheme for the database layout and use inclusion proofs, then basically this statement can be translated into an inclusion proof that you can submit to the blockchain, and a smart contract can evaluate that particular statement is true. And since that is a mechanistic process that you can it simply answers yes or no, it can be used in a witness contract, in a swap, swear, and swindle game. So when the database indexer registers their service to index a particular primary data source, then they commit to a service contract, which then you can challenge that service context if you find that the data item was not included in the index. So I don't know if this is more or less clear. So that's one aspect that we're trying to integrate, and this is kind of very important, because all the other solutions that we see in the space for all these data gateways, including big chain and also IPRD, the IPFS data solution. They are very, very nice I'll give you some features that are very important in those paradigms, but they seem to have this like missing piece where you can actually have provability of the database operations and provability of query responses. So IPRD, for example, is a very evolved database structure, which we definitely rely on. So we have, ours is basically an extension of that. What's included in that? It's basically a JSON-like attribute value structure scheme, which uses linked. So the embedded structures in the JSONs can be referred to with the content address of the embedded object, which means that it's genuinely provides integrity protection over your data, and the important thing is with this content address links is that if you map these data structures into an in-memory data structure, then these links are typically pointers, and using content addresses, these pointers can be directly mapped to references in a distributed storage. So given this database layout, it immediately defines how to store such huge graph databases in a decentralized storage system. So and this gives this leads me to the next important point, which is also going to be a relatively novel feature in our framework, which is that since the pointers are references to the to content addresses in the distributed storage, all the database operation or the data structure operations like merge or delete or add, they can this similar way to how they are defined on pointers as like recursive functions to across these embedded structures. They simply map to network protocols. So when you define an add or merge function over an in-memory database, and you use pointers to like children to define the next level in the recursion. The same way you can define protocols over the swarm network to carry out those operations. And this is a very interesting approach, because it allows for basically outsourcing to the network an update to the database. So you don't have to pre-compute yourself an addition in a huge data graph, but you just simply send a message to the address that corresponds to the root hash of the database with the request that please add this extra item to the database. And what it does, it simply looks up in its children where the data has to be added, and simply looks up a content address that points to that intermediate node, and forwards a message to them. So it's like basically instead of recursing on an in-memory structure, it's recursing as a sequence of relayed messages. So basically, as you can see, this topic kind of links all the components we were talking about today together, because this database operations can be these database operations can be described as PSS protocols, basically, and in the same way as PSS messaging is incentivized, these database services are also when I send a message to update, it's basically a service request that we talked about in the Swapsware and Swindle game context. These are kind of promissory notes, basically, that become mature and become rewardable when the update happens, and you can formulate proper verification criteria with a witness contract when to verify that a particular update happened. And in the same way as other services, if you fail to comply with the service promise that you index a particular data source, then you can be challenged on the blockchain, and you basically stand to lose your deposit as a result. So these are the things that I wanted to mention, and sorry, I'm a bit running out of steam now, so I hope you don't mind that I will just cut it short.